Something that you probably don't know about me is that I'm terrified of speaking in English. The reason for that comes from the 2012 International Young Physicist Tournament, or at least that's what I think. I am highly insecure and I'm doubting myself a lot because I never, at least up until recently, had the chance to speak in English and giving a presentation in English. This is because back then, when I was between 11th and 12th grade, my presentation wasn't very good. The Young Physicist Tournament consists of presenting a task which you've had months to solve within a very strict limit of 12 minutes. All I wanted was that I'm not the one who has to go first. Various teams challenge each other on the list of problems, and all I wanted is that I don't go first. What happened? We picked a number. There was a lottery. The jury decided that we will be one of the teams which are going to present on the very first battle, and then when the time came to present, my problem was picked. I had a couple of problems, but one of them was picked from the opponent's team, and I had 5 minutes to prepare my present. Actually, we had 1 minute to decide whether we are going to go through with it or decline. And that's when things got rough. Our team captain took a brief look over my presentation. She remembered that this is not a good presentation, and we declined the challenge. This was probably a good decision about our Bulgarian team. We weren't going to get a lot of points, although we got some penalties because we declined too many challenges, but still, probably I should have presented back then, because even though our team would have lost a few points, I wouldn't have had all this trouble during the last 8 years. Thankfully though, within the Masterclass for the 2020 FameLab contest, we had to do presentations in English. And okay, you're going to see the first presentation in English that I have ever given officially to anyone. And here it is.
Guys, how did you know when to join the meeting? I bet that you looked at the time and date. They are dictated by the most important object in our sky, which is the sun. I'm hearing myself. Which is the sun. Let's imagine that we are an historian who is looking at our research of the exploration of the sun. First, we come across some ancient tablet which says that the sun is clearly our god. It gives us heat and warmth, which are essential to life. And even in the darkest of nights, we create fires just to mimic the sun. But that can't be right. There are thousands of stars. Not all of them are gods, all doing the same thing. Oh, here is an ancient paper, now a note, which says that the sun is not our god, but is created by God from some magical substance which is glowing. Okay, this seems plausible. It's not like we can go and touch it to see. Not until we find some books by Isaac Newton, who proved that the gravity that holds us here on the ground is the same that keeps the Earth orbiting around the sun. So the physics on the sun must be the same as the physics here on Earth. During the 18th century and the 19th century, there were a lot of scientific articles written about what the sun must be made of, since it must be made of earthly materials. The physics is the same. Scientists tried to calculate how long would the sun last if it was made up of coal and oxygen, and it turns out that it will be burning for about 1500 years, which can be correct. The Romans didn't conquer most of the known world in complete darkness. Thankfully, we come across an article written by the physicist Helmholtz, who thought that since the sun is attracting us, it's probably attracting itself. And if the sun is shrinking and giving off energy due to its shrinking, it can sustain its brightness. But he calculated that the sun must have been as big as the Earth's orbit 100 million of years ago, which seems alright, until we read some other articles that scientists have found fossils and minerals which are more than 100 million years old. This is a serious problem, at least until the 20th century. Now, when we read out articles from the 20th century, we are not looking like this, we're looking like this on a computer. And we read that combining 4 hydrogen nuclei into a helium nucleus gives off energy. Probably this is the reaction that sustains the sun. After all, scientists discovered that that's what it's made of. But turns out that the sun is not hot enough to sustain this reaction. It's 5,000 to 6,000 degrees Celsius. But then another astronomer came to the scene, Arthur Eddington, who calculated that if the sun was a big cloud of gas and dust in the beginning, just like Helmholtz calculated, when it shrinks, it would heat up and give away energy. And in its core, the sun must be 15 million degrees Celsius hot. That's how we know how the sun works, and that's what we learned from our historical research. Thank you.
As you may know from my other videos, the FameLab presentations consist of exactly 3-minute talk with no slides, probably something you can carry with you, a balloon, a pencil. You can demonstrate something, but you can't use slides, you can't print them, for example. A very good friend of mine, Yves Wiliev, is within his last year of his PhD in Sofia University in theoretical physics, and he is also a participant in this year's FameLab contest. So here is his presentation.
I want to talk about string theory once again. And a lot of people have problems with string theory. One of the problems they have is that string theory seems to live in this high number of dimensions. So 26 or 10, maybe you've heard 11. But where does that number come from? And why is it that for most string theories, at least, it's not really a problem? Well, first, imagine a particle. So I have this guitar pick, which is going to be a particle. When it moves through space and time, it tracks a trajectory, which we call a world line. Well, a string is not really a particle. A string has length, so this is a one-dimensional object, imagine it. When it moves through space-time, what it sweeps away is some kind of two-dimensional surface, so a sheet. We call this a world sheet. And it turns out the string theory can be, let's say, imagined and described in terms of some dynamics, some movement along this world sheet. And if strings were classical objects, that's going to be fine, but strings are quantum objects. We're talking about quantum strings. And it turns out that this worksheet has a very particular thing about it, that if the strings were quantum objects, it seems to matter how we parameterize this surface. What does that mean? It means that it matters if we take like this grid and describe coordinates on this grid, or if you take like this grid and we describe coordinates on this grid. But that's not physical. Physics should not depend on the observer. It should not depend on me, it should not depend on you, it should not depend on anyone who is just arbitrarily measuring something. In order to actually fix that, we have to do some maths, doing maths, and again, we arrive at some equation that tells us that in order for the strings this to equal this, they have to live in a big space-time of 26 dimensions. Or if we include supersymmetry, it turns out it's going to be at 10 dimensions. So how is that not a problem? Well, first of all, string theory is the only theory that we know that actually self-imposes a number of dimensions on which it's going to live. So if you take the standard model of elementary particles, which is the most successful theory that we have now, it lives in 4 dimensions. But that number, 4, doesn't come from anywhere. It comes from observations, but of course we know that our senses, our experiments, and our things can be deceived. So I think that what a lot of people perceive as a strict flaw of string theory is, in some sense, its wackiest, wobbliest achievement. So thank you very much.
Now that this happened, I can create a playlist which will consist of videos in English, and you can see them. You can share this playlist to your friends which do not speak Bulgarian, and they can get at least a little glimpse of what happens here in this channel. In conclusion, the reason that I am not doing videos in English is because there are a lot of English channels and there is no need for another one. But up until recently, at least, when Curious Bunch created their channel, there weren't really any channels talking about physics in Bulgaria. So I will continue making videos in English, but in some weird situations, when for example our presentations were in English to begin with, and when the video would be really awkward if there are two languages, I am going to go for English. And I expect this to happen very rarely, but still the channel is not new. It's been more than 3 years now, and I feel that with time it will accumulate at least some videos which you will be able to show to your non-Bulgarian speaking friends. So that's pretty much it. As always, I would like to thank my patrons on Patreon. I've heard this line so many times from other YouTubers, I have never said it myself, but thanks to them this channel exists. So yeah, that's pretty much it. Here you can see the playlist with videos in English, and you can click the subscribe button hoping for the next video in English. So that's it. Thank you.